Okay. Well, it's yeah. Sometimes I think it's with the touchpad that it's showing like a click drag, like it's holding down a click.
Are you using a mouse?
I'm using a mouse and a touchpad, and then I've got the touchpad on the laptop.
You're able to disable the mouse pad.
Yeah, I may have to do something like that. Yeah, so we're gonna finish up the interesting liquid phase diagrams, and then we'll get into the solid phase diagrams today. And then next time we'll do the Hexane solubility parameters, which I'll need to post some notes for that, so that you'll be able to bring those to class. All right, so here we have the partially miscible system that we discussed last time, which was with the upper critical solution temperature. So this kind of makes sense if you think about it. If you've got solvents that like each other, like themselves more than they like the other component in that mixture, that at low temperatures they're going to phase separate because they're more stable in themselves than they are in the mixture. But if you raise the temperature, you can disrupt those self-attractions of solution A with A and B with B, and so that spontaneously they mix just based upon entropy. So raising the temperature increases the entropy, and the entropy can drive mixing. So is everybody clear really where the upper critical solution temperature comes from? It's really at lower temperatures, the attractions of a solvent to itself dominate. And in this case, this is benzene and hexane. So which of those solvents is most likely to be the one that causes phase separation?
Nitrobenzene.
Yeah, and so why do you say nitrobenzene?
Aromatic has high interactions, maybe it wants to like stack more.
Yeah, so you have a drastic difference in dispersion. So this electron cloud, the aromatic electron cloud, is a disperser, or London dispersion forces are really active in a polarizable molecule. So when those clouds get together, they can interact with each other, kind of oscillate and create instantaneous dipole moments. That's sort of the source of dispersion interactions, is this polarizable electron cloud. So as they start to oscillate, they can get in sync with each other, and there's an attractive potential there, so they can stack together. But there's also that nitro group. So that even though it's very negative, it's also full of electrons, it does make the molecule asymmetric. And so there will be some small polar component to that, especially compared to hexane. So hexane is non-polarizable. I mean, it's just surrounded by those hydrogens. Most of the electron density is pulled in towards the carbons, and that cloud is not very floppy. The molecule is floppy, but the electron cloud is pretty rigid. Those CH bonds are tight, and they don't have a lot of electron density outside the hydrogens. So hexane really doesn't care much about hexane, and nitrobenzene likes nitrobenzene. So it's nitrobenzene that's really excluding the hexane. Okay, and we kind of see that in the nitrobenzene-rich layer. You see, it's more pure than the hexane-rich layer. The nitrobenzene-rich layer is on the right. And when it's cold, it's excluding the hexane. It's more pure. It's 80% nitrobenzene. And that's what happens with oil and water. If you think about oil and water, water hydrogen bonds to itself. It's polar. Okay, the oxygen is, polarizable. So it's pretty high in dispersion, pretty high in polarity, pretty high in hydrogen bonding, very high in hydrogen bonding. And so if there's an oil molecule in the way, you've had to get those polar components farther apart. But if that oil just happens to slip out of the way, water snaps into place, and then that non-polar molecule can't get back in between the water. So as soon as those molecules slide out of the way of water, water associates with itself and the oil separates. It just shoves it out of solution. So it's water that's responsible for water and oil not mixing. So the point of this whole exercise is to think about the molecules, ions, down to the very atoms to understand your chemistry. Because that'll give you intuition. As you're thinking about a system you haven't come across, think, how does this go about? What's happening at the molecular level? And the more you can do that, the better chemist you're going to be. So look at this one. Very strange. Okay, so this is a temperature composition phase diagram, and this is mole fraction of triethylamine in water. So triethylamine in water. And so this one has a lower critical solution temperature. So that's really strange, isn't it? So I'm not doing that. Okay, which way do I need to go? This is great on the video. Yeah, it clicked through. I didn't touch. So you see, it's still. I'm just moving the mouse. I'm not dragging. Okay, let's see if I can do this. It's not responding to the video. Yeah, so let's look at this one. Yeah, so it has a lower critical solution temperature. So let's take a chance. You've already spoken, so someone else. Let's take a chance on explaining why this might have a lower critical solution temperature.
Yeah, if we kill all the auxiliary plugins and try to pull them. So you read it?
No. It's just walking to it and tighten up. There we go. All right, right there. So why would this solution be miscible at low temperature and not at higher temperatures? What's triethylamine?
It has limited hydrogen bonding.
Yeah, so you could have this. So that would favor miscibility. And that's good. So, but it's temperature dependent. So this is probably the explanation of the miscibility, wherever there is miscibility. So now take this and start raising the temperature.
Would the boiling point have a factor?
It might. The boiling point is really how triethylamine is interacting with itself and water is interacting with itself. So you know water has such a huge high boiling point because of the hydrogen bonding. Yeah. And so triethylamine by itself can't really hydrogen bond to itself because the CH bonds don't really hydrogen bond that well. Yeah. The carbon doesn't pull enough electron density away from the hydrogen to make it exposed on the other side. That's what's really driving hydrogen bonding for this hydrogen on water. The oxygen pulls so much of the electron density towards the oxygen that this proton is visible from another lone pair. And so that's that association that snaps into place. And it's for the smallest atoms, nitrogen and oxygen, that really pull in fluorine.
But is there very electronegative?
Yeah, that's the term. So fluorine, very electronegative, nitrogen, oxygen.
So a while ago when you talked about the pockets being formed,
Yes?
could the energetics of water decrease the strength of the hydrogen bonds between water itself just because of the...
Yeah, that's at really high temperature. Yeah, in water. I mean, that's what's going on when it boils, right? So you're breaking up those hydrogen bonds in water. So when you get to really high temperature, the hydrogen bonding in water becomes less effective because the kinetic energy of the molecules. So follow kinetic energy. Look at this complex and tell me what kinetic energy is going to do with it. Yeah, go with that. Yeah. Remember the vibrational frequencies. Okay, so goodness, these caps. there's another constant in here, but mu, K over mu. So K is the force constant, pi, I think. Okay. Yeah, so K is the force constant for vibration, and mu is the mass, the reduced mass. And so if you have heavy masses, you're going to have a low vibrational frequency. Remember we talked about active vibrational frequencies? CH stretches, 3,000 wave numbers, because you got really tiny mass, and it's a stretch, so it's a high force constant. Okay, so you're not going to activate the CH stretches or the OH stretches, so forget about them. Okay, but what other kinds of motions are there in a molecule?
Bends.
All of those bends. Which one of these has more bending modes? That one. Okay, and when you're bending a whole ethyl group, what's the mass? You're throwing away around a huge mass. And what's the restoration force of that mass? Like when it's twisting around this bond, is there a huge force constant for that? How much energy do you think it takes to just rotate that ethyl group around that sigma bond? Does that take a lot of force? No. And so that's going to be your most temperature active mode. At low temperatures, that mode's not going to be very active, but eventually you're going to reach a temperature where that mode just starts going crazy. You see? And so there's 3 of those. I mean, you're going to start moving up, and then you've got the methyl twist, and those things are going to do like that. And so you're really going to be shaking that nitrogen and making it difficult for this linear hydrogen bond to hold on. Yeah, so when this association gets disrupted, what happens then to the water? As soon as it gets one of these molecules out of the way, it excludes it. So above a certain temperature, when these vibrational modes become active, then this just becomes like a hydrocarbon molecule. It just becomes oily. There's really no way for it to maintain that association with water, and so water excludes it. It's first chance it gets. If it moves out of the way between 2 water molecules, they snap together, and this triethylamine just keeps moving to the surface, to the interface, and gets excluded. You follow it? You follow the progression? Down at low temperatures, we can have this complex, this weakly bonded complex, and you start to raise the temperature. You've got kinetic energy between these 2 molecules increasing, and then you've got these vibrational modes that are low frequency that start to get active. And you could test this by going to Gaussian and calculating what those dihedral motions are. You could animate them and see what the vibrational frequency was. And you could see what temperature, convert it to temperature, and see what temperature they become active. And that would be one way to kind of see, if you wanted to see what the lower critical solution temperatures were for a series of compounds, you could then correlate those with the lowest vibrational modes and see if that correlates. Okay. So thermal motion breaks up this interaction and phase separation occurs. There's one more that's even stranger. This is the lower critical solution temperature. This is nicotine. So it has both. It has a lower critical solution temperature and a higher critical solution temperature. Now these are quite high temperatures. Notice low is 61 degrees C, and the other is 210. So this is obviously still in the liquid phase. So this is going to be at an elevated pressure. So water's at 210 degrees Celsius, so it's above its boiling point, but that means that the pressure is, since it's still liquid, the pressure is higher than 1 atmosphere. So let's think about this again. Nicotine, it's a caffeine-like molecule. It's one of those, what are those ring systems called? Yeah. And so they, at low temperatures, it's going to have, again, some hydrogen bonding that can occur, this weakly bonded complex, so that it's miscible with water, but you raise the temperature, that complex becomes less favorable, and so water excludes nicotine. But then you asked about, at high enough temperatures, does the water hydrogen bonding start to get disrupted? Yes. And so once the water's hydrogen bonding starts getting disrupted, then it can't exclude nicotine as well. And so then entropy finally drives them together. So they mix above the upper critical solution temperature because of entropy. And below they mix because there's some sort of weakly bonded complex. And so this is just that balance between whether a solvent likes itself or, you know, more than its mixture partner or its other component, or, you know, whether they have no real association with themselves and they can mix by entropy. Anything that you need clarification on this one? Again, if I dropped you anywhere in this diagram, would you be able to tell me what phase you were in and what, you know, you were, it's a TX phase diagram. This is the only one that has a circle in it. Okay.
Is there any opposites where the P1 is in the circle and the P2 is out of the circle?
No, no. And you start with the pure substances. You go to the pure substances, those are homogeneous. So those are P1, one phase. And you come in and you hit a line. You're like, okay, that must be where phase separation occurs.
Double line around.
Yeah, so you could come in from the side of pure water, and you come in, you hit that deal, like if you're at a certain temperature and you're just increasing the composition of nicotine. And so you could follow an isotherm through this. Pick a temperature, walk through, and you're mixing in nicotine, and all of a sudden it forms two layers. And you could, you know, that's where that dashed line is, it's about at 20%, you see. So you can get up to 20% nicotine in water at that temperature. If you go any higher, you're going to have two layers. So that's the solubility of nicotine in water at that temperature. So there's another piece of information you could get from this chart. It's the solubility of nicotine in water. And it's temperature dependent, as you can see.
You just use the level rule, it's how much is it.
Yeah, if you go past that, then you're going to have two layers, and this will tell you the concentration of each layer. Yeah. And then you can look over there on the far right, and that would be the solubility of water in nicotine. You know, 1 minus that. So it looks like, you know, about 85%. So if we're over on this side, let me get the pointer. If we're over on this side, you know, it's a little bit more than 80%. So that's, you know, like 15 or 18% water and nicotine. So that'd be the solubility of water and nicotine. I mean, you could get it miscible if it was at cold temperatures, but if you're at, let's say this is room temperature, okay? If you're at that temperature, then that's the solubility of nicotine in water. And if I said, all right, I'll drop you in here at a 50-50 concentration at that dashed line temperature, do the lever rule and figure out what's in each phase. So you're right here at 50-50, and you draw your two lines left and right, you know, and you can figure it out in terms of how many moles were in each phase, and so on, just like we did with the previous one with nitrobenzene and hexane.
Why are they at temperatures beta for Kelvin?
Say that again?
Why are they using beta for temperature?
I don't know. Yeah, it's just the source of the figure. Yeah, no, that's strange. Okay, so then we have distillation of partially miscible fluids. So we're adding the vapor phase on top of this. So we were just in the total, you know, all liquid phase for the last two phase diagrams, last three. And now we're putting the vapor back on top. So there's two possibilities: the upper critical solution temperature, then you have a homogeneous region, and then you have the boiling behavior. So up here at the top, you have the boiling behavior here. Here's the upper critical solution temperature. And so let's just walk from A1 down to B3. So we have a solution of mostly B, and we boil it. And we do a simple distillation, so we collect the condensate. If we stop at this temperature, it's homogeneous. If we come all the way down, then we have two layers in our collection flask. And so it's a little strange if you think about it. You've got a homogeneous solution, you distill it, simple distillation, and then you look at the collection flask and you have two layers.
And we can use the level to see how much B is in there.
Yeah, and so one of those layers is going to be pretty small. So the B-rich layer is most abundant, and the A-rich layer is way over here, and it's a very small layer because of the lever rule. Yeah. If we did a fractional distillation, our concentration would be right here at the azeotrope. So we went up here, it evaporated, condensed in the fractioning column, and re-evaporated, so reboiled higher in the column, and then condensed, and then reboiled and condensed, reboiled, and then up here at the collection, you know, the thermometer and the adapter and then the condenser, we collect this fraction, and it comes down, and it would be 2 layers. But it would be rich in A. You know, that would be the most abundant layer. It would be a B-rich layer that's smaller. I see nods. Yeah. Okay, good. Now the one on the right is really strange because they don't have an upper critical solution temperature. It still boils, but you've got a 2-phased mixture and then it boils as 2 phases. Now remember that you can't, you know, when it's boiling, it's at equilibrium. So the Gibbs energy or chemical potential in all phases, including both layers and the vapor phase, are equal. Okay, so both layers are in equilibrium with the vapor, even though one's on top, one's on bottom. So when those cavities form and they're flowing up through the 2-phase liquid, there's exchange, and the vapor phase is reaching its equilibrium concentrations in both A and B, and it goes up into the vapor phase. But this would be the boiling point of the 2-phase region right here. So, you know, if we were, let's see, where do we want to go in this figure? Let's just pick B3 and kind of go backwards. If we come up here to B3 and we boil that, this is going to be the boiling point, and the vapor composition is here, and the liquid composition is the lever rule between there and there. Okay. So that's probably the most complicated behavior, is right there when you have the 2-phase liquid boiling. The liquid is governed by the black lines here. Okay, and the vapor is covered by these 2 blue lines.
So all the horizontal ones are just tie lines?
These are all just tie lines, yes. Yeah. So yes, that's a good point. We could draw this one like this. Without any tie lines. And that shows you where the phase boundaries are. So this whole region in here is P equals 2, and this is P equals 1, P equals 1, P equals 1.
So you said going from B3 toward B1, it stops at a level equal to E2?
Here's the deal. So let me draw this bigger, because if I point at the screen, you don't capture it on the video. So I'm going to try to do it on the board since I've lost my tablet. Okay. So I'm better at art with my full arm than that little Wacom tablet. So maybe it'll work out. Okay. So we have this situation. This is the vapor composition. Okay. And so let me use different colors to show the tie lines. Okay. So there's a tie line right here. It connects this eutectic mixture. This is an E. Notice it's not an azeotrope, it's a eutectic mixture, which will come in. It's kind of strange. Eutectics are technically are most often talked about with solid phase diagrams, but this is behaving like a solid phase diagram, so we still call it eutectic. Okay. If I'm boiling right here, is this what you were asking about?
Mm-hmm.
Okay, if I'm boiling right here, then I've got a liquid there, and a vapor there. So that tie line has 3 spots on it. This is the composition of the vapor. And this is layer 1. I guess the L is probably not good. So, but can I use instead? I'll do distance, right? D1. Does that make sense? D2. Instead of putting L's for the lengths of those tie lines. And this is vapor. So that's the vapor composition above the two-phase liquid. Oh. Yeah. So our liquid phase, our N1, D1 is equal to N2, D2. To figure out how many of these moles we have in this phase, D1 and D2. And then the composition of the vapor at equilibrium with those two liquid phases is right here, the vapor composition. And they're calling that E. Like,
how do we figure out how many moles of...
How many moles at equilibrium would be in the vapor? Then we would have we would have this here, D3. So we'd have to figure out 3 weights on that line.
Okay.
And it would be tricky because you'd have all of the moles add up to the total moles, okay? And so that's equation 1. Then this equation 2 would be the lever rule for these. So if these are both on one side of the fulcrum, so we've got a third number of moles in the vapor phase. And so we have 2 equations but 3 unknowns. And so we couldn't solve that very easily. We'd have to find another third relationship to figure out what that third component is. If we go above that line, it gets simpler because we've lost this layer. If we're up here, and that's our fulcrum, then we go to the nearest vertical line and stop. If we're up here, then we have vapor-liquid equilibrium between, like if this is XB, dirty B, and vapor only. But this middle region would be the most difficult to figure out what the relative amounts are in each.
But D2 is overlapping with D3, so would you take away D3?
No, because it's distance from the fulcrum, so it's just going to make that really small. D2 is really small. And so what you might assume, if you had to, like if your arm was twisted and you had to come up with this, you might assume that N2 was really small. And so then N3 and N1 would be your major components because this is the fulcrum. And so these would be the 2 largest amounts of moles. So again, that would be your third equation would be to set N2 equal to 0 and then solve for N3 and N1. Yeah. So that's how, if I was if I had to solve that, that would be the assumption that I would make. I would say, assuming this layer is so small that we wouldn't even see it, let's solve for the vapor-liquid equilibrium for just these 2 pieces. Yeah. So this is also a strange one because it's very difficult to, separate these things. I mean, it's effectively, you could use a separatory funnel if you were somewhere in the middle. That's pretty easy. But in terms of distillation and really purifying them, it's very difficult. You're going to either get a layer that is that dirty or a layer that's that dirty. Kind of looks like a rabbit to me. That's the 2 ears. Okay. Is this going to work? Nope. And it was just talking through different examples of distillation. So let's look at liquid solid phase diagrams. Now, if you think about solutions, these are binary mixtures. These are solution phase diagrams, but yet they could be a solid solution. Any homogeneous mixture is a solution, okay? And this is a homogeneous mixture. This is a brass key, but brass is a solution of zinc and copper. And so you could just mix those together in any proportion, and all those different proportions are still called brass. Okay, now there's different kinds, different grades. There might be specifications on the strengths and so on of the different alloys, but this is a homogeneous solution. So if I scraped this piece off, I'd get the same composition as if I scraped the top piece off or the side piece. No matter where I scoop with my spoon, I get the same composition. So that's what we mean by homogeneous. Okay, so it's kind of strange to think I have solutions in my pocket. Open my door with solutions, homogeneous solutions. Yeah, it's weird. Yeah. So this is what we're talking about. We're talking about solid-liquid equilibrium, and the melting points of these alloys or mixtures of solid substances are very dependent upon their composition. In fact, that is a huge part of material science, is balancing the melting points. Not just material science like for technical applications, but milk chocolate. Okay, so we have a differential scanning calorimeter upstairs that was made by Mettler Toledo, and the guy, when he was trying to get us to buy the instrument, came by and did a little demo for my PChem class. Showed up, and he brought chocolate, Lindt chocolate, Lindt, Swiss chocolate, and gave it out to the class. Everybody was excited about that. And he said, this chocolate company in Switzerland pretty much pays our bills as a whole company. So Mettler Toledo's division that sells differential scanning calorimetry, they pay all their salaries, all the buildings and everything, all their rent, just based on the Swiss chocolate industry. Because every change they make to that homogeneous mixture affects the melting point. And so they do differential scanning calorimetry on their chocolate all the time as quality control. Because it's got to ship from A to B, it's got to have a certain texture in your mouth. You want it to not melt too fast, but not too slowly, you know. And so there's a fine line, and it's probably trade secrets. I mean, I don't even know what those melting points are that they're looking for, but, you know, even M&Ms, they say melt in your mouth, not in your hands. You ever hear that phrase? It was their company, you know, catchphrase for a long time. And so, anybody ever leave a pack of M&Ms in the car? Melts in your car too, but not in your hands. It just, the little shell will crack open, all the chocolate melts out. Anyway, I like the shell the best, so I like to take all the shell pieces out. Yeah, so I've done that. True story. So what we have here is, again, start with the axes: temperature, vertical axis, x-axis is composition, mole fraction of B. So far to the right is pure B. So always start with the pure components. So if I've got pure B and I go straight up that line, where that hit that blue line, that's the melting point of pure B. Just like in the vapor diagram, that's the boiling point of B. So you just take your pure components and go straight up, and where that, you see that phase boundary. And again, all the horizontal lines are tie lines in this graph. So the only ones that are not tie lines are these curves. This is the liquid solid phase boundary right here. The curved lines are the phase boundaries. And then over here, this is the melting point of pure A. You go all the way up to the top, and that's the melting point of pure A. So that's the first thing you do. Just like sort of look at it and say, okay, now I understand where A melts and where B melts. And sometimes those are labeled. And then you have the minimum melting point, which is the eutectic mixture. So that's the definition of a eutectic. It's just that, you know, the mixture at the lowest boiling point between two pure substances. And why would it have the lowest melting point? You know, what is it that makes the eutectic the lowest melting point? I mean, maybe it's kind of a difficult question to answer, but what is causing the melting is entropy. Okay, and so that's going to be the mixture that has the highest entropy. And so it's going to be the one that melts the soonest. So this is the combination of A and B. If you've got just essentially spherical atoms that don't really care about each other, they're pretty similar in terms of their you know, electron clouds and so on, their chemistry, they'll probably melt. There'll probably be a eutectic at 50-50. Right, because there's really no difference in A and B. So the one with the highest entropy is the 50-50 mixture, And so that would be your lowest melting point. Okay. So any asymmetry to this is kind of giving you a clue as to the differences in the two atoms, two substances that are mixing together. And so let's go through this phase diagram and draw some pictures. I'm a very visual person, so I like to see what's going on picture-wise. So this is the solid all down in this region, liquid all up here. If we were to draw the, partial miscibility and the boiling points, we'd just be up on the 3rd floor. Okay, so this is the same TX phase diagram, we're just down in the basement. So we're looking at the solid liquid where it melts and freezes. So if we take, let's start up here and go down. So we take this spot here, A1, and we want to cool it down. When we get to this point, what starts to happen?
Solid B and liquid A and B.
Yeah, so if we had a little microscope and we're looking at this as we cool it down, at this point, we start to see a little grain of B form. And we have A liquid.
Only A liquid or A and B liquid?
And B liquid, yeah, thank you. And B liquid. So we have, the liquid has this composition, and the solid is B solid, it's over here, and it's mostly liquid. So we have just a tiny little, the very first nucleation of solid B starts to form. We're following an isopleph, so we're coming all the way down. And so we get to right here, and we do the tie line. And we go left and right until we hit a boundary. Either the pure substance wall over there, or one of the liquid boundaries here. Okay. Yeah, so we have B, let's draw some B up here. It's beyond our microscope there. So let me draw A. Since we're losing B, we have a lot of A in our liquid. You see, it's getting more enriched in A as we're pulling B out. But you see that A is getting more concentrated in the liquid. And once we hit the eutectic, so this one is, once we hit the eutectic, we start to form some A over here. The eutectic is still liquid solid equilibrium, but if we go just below that, we start to precipitate A. And so let's go below that here and draw our picture. Oh, wait. Microscope. Time to go. Okay. So we have B solid precipitated out, and then we hit the eutectic point, and we pause there until B and then the rest of A turns solid. And once A is now fully solid, we can go cooler. But we can't go past that point until we finish precipitating all of A. If we go below the eutectic, it's all solid. And so we can't get below it. And so we'll have this pause in our temperature until A is finished precipitating. and we have solid. And that's called the eutectic pause. So we're cooling this mixture down. We have a very smooth freezing point until we get to the eutectic pause, and we'll sit there for a little bit, and we'll see, it'll look like it's freezing there, but we will already have had some solid B coming out. And then we'll pause there until all the rest of the A precipitates out, and then we can cool our solids further. Same with the melting. If we're melting this, we get to that and A starts to melt. And then the liquid phase has a little bit of B melted in it too. We have the eutectic mixture. And then up here, we're just melting the remaining amount of B. And so this whole region from here to there is melting. If you think about the temperature range, this is temperature. That's a huge temperature range. Do you remember from organic chemistry, doing melting points? What were you trying to determine with your melting points? The purity of your substance. Look at that melting range. That is not a pure substance. We're way over here. If you're a pure B, bing, there's your melting point. It's a point. But if you're not pure, you have a range of melting points. And it's just hard to tell. You still see some crystals in your capillary tube, and there's some wet spots, and you're like, is it melting yet or not? It's strange. I see some melted stuff and some not melted stuff. It's because it's not pure. If it were pure, it would be solid, 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 liquid. I missed it. Check the temperature. Don't go too fast. You know what I'm talking about. You've all done this. Same thing with A. You get up here, melting point of A, different than B. But anywhere in between, you have this mess, this melting range. And if you were to stop it and take pictures, and be able to tell the difference between A and B, that's what you would see. That's a good place to stop.